Thank you. Good afternoon, everybody. As the chairman said, my name is Jalal. I'm from Max Planck Institute for Plasma Physics from Munich. I'm working also in the VECMA project with Derek and Robin and others. And now I will present how we are using this tool in the fusion application. So talk it will be about EQ and static quantification in multiscale simulation, because we have this application is multiscale application, and this is my talk, and I will start that. No, it's with this one. No, sorry.
Oh, yeah, that
doesn't work. This one for. So for the plasma, so it's an analyzed gas. It's now that it's the fourth state of matter. You can find it in solar wind and lightning and other phenomena. And thanks to for example, in solar wind, in the plasma with the fusion provide the energy and is high energy, and we want now to reproduce this energy using fusion of plasma, for example, in this nuclear machine here, and this is a tokamak, and it's quite challenging subject in physics and also in scientific computing. And we have exist several codes to modeling and simulate physical phenomena in the fusion plasma. And what we have we have a code. It is multi-physics code using several codes component. We have first one is transport code. It's 1D code, and it's run in second. The second code is equilibrium code. It's for the geometrical equilibrium for the flux, and it's 2D code, and it's run in seconds. The first one is millisecond, and this one is seconds. And the last one is turbulence code, and it's 3D, but it's run from minutes to hours, and it's parallel. The two codes are in serial. And this one, the last one, just translation for to plug to do the cycle, and it's also 1D code and run in seconds. And here we have some source profile, and data from experiment that we can check. And in this multi-scale, we have macro part and macro part, and we have also sources of uncertainties. We have uncertainties here in the sources. Of course, uncertainty we do experimentation, and we have also uncertainty inside the codes. For example, turbulence code, they have some stochastic hypotheses that they produce uncertainties. And the goal here, how to quantify the uncertainty, because it will be propagated in this workflow. So I will present briefly the application workflow, what we start now to study, and I will give you two approaches, the EQ approaches that we will use. Before the conclusion, I will give some results for the current model we are using. So the simplified model that we will start with, it's this one. We are using the three codes: transport, equilibrium, and turbulence. As you showed, it's cycling. We have a multi-scale and cycling component, and the uncertainties we have it here in the source and in the turbulence code. So we have external and internal uncertainties. So how we want to use to quantify uncertainties? Well, we will use the primary chaos expansion, because we don't want to modify the codes, just like black box. It's a very complicated code in production. So we start using PCE, but we have two approaches. The first one is fully non-intrusive method. So approach. So a single black box for all codes. So here we have one black box for all codes, for the three codes here. And the second pattern is the semi-intrusive. So each black box, each code is like one box, one black box. So what for, I think, I don't know if you are familiar for the polemic Gauss expansion. So just the output, the result of it's, you can do approximation using, for example, here, if y is the output, approximation y here we have three parameters, three variables, space, time, and also q, it's the uncertain parameter. And we can expand it to this using the polemic expansion here with Pn is the polynomials and Cn are the coefficients. The number of expansion, it's depend of P, small p is degree of polynomial, and also depend of the number of uncertain parameter here. So we are using this, and we have some properties, interesting properties for this polynomial Gauss expansion. So the polynomials are orthogonal because the assumption that the input parameters are independent. So we can have this polynomials orthogonal, and for each density, for example, for Gaussian density, we have Hermite polynomial, and for uniform also we have others, and the literature we can have it. To compute the coefficient Cn, we use just this scalar product here. We use on the integral this one, and we have lots of methods to compute them. So for in the toolkit we have the Gauss-Pay provide quadrature rules, routines to compute them. And the end, we can compute also the means, the low mean and variance, the low moment. So using just the coefficients here, just simple one is the means, the first coefficient C0, and the variance is the sum using the normalized factor defined by this formula. So now I will use the first approach. It's all my workflow is like one black box here. And we assume that we have uncertainties in sources and in boundary condition. So we have here the source, it's physical input. We have amplitude in the source term that's uncertain, and also width and the position. Where is the, and mainly here it will be in the core of the plasma, it's in the center. And we have also two parameter, uncertain parameters, Ti and Te. It's the temperature of ion and the electron inside the plasma, and we have, because we fix the parameter, the boundary condition, it's imposed directly, and we have also uncertainties in this one. The first one is Gaussian, I think also the second one is Gaussian, and we quantify the output. It will be also the temperature of electron and temperature of ion, and also we can have other quantities like pressure or density or other physical parameters. So the implementation we are using is EQ library, so that presented by Robin. And now I will show just some results here. So here the uncertainty in the sources. So we have just three parameters, and here in the core of plasma, it's here it's in the center of the plasma, and here it's the edge. So we have it's Gaussian here, and the uncertainty is propagated just here until, for example, in the center here, and this one is no uncertainty in the edge. And we can show here, for example, for some sensitivity analysis here, we have I think this one is the amplitude, this second one is the position, and the third one is the width. So we know that there's no influence of the last parameter here. And the second thing is if you add other two parameters, so the initial condition in the age of temperature of ion electron. So here we will have another uncertainty here. So it's not, we cannot show it, but it's here the variance is bigger. And also, if we check the Sobol coefficients, so here the first one is like the previous Sobols for when we have two parameters. So here the amplitude, so and the position and the width here, and also we have here the we impose temperature in the boundary, and here we are looking in the electron temperature here, and the temperature electron is the main influence come from this temperature of electron. So this simulation, it's run with an Emissive EQ. I have 5 parameters, so it will be using polynomial degree 4, so it's 6 power 5 run. The first thing I use it just with the VQ. I run it in the local machine and the cluster, and now today I think Onnie in Munich, she used it also pilot job, and it's also available in the tutorial. The second approach, because we know that we will have this third code, turbulence code, it's B code, so we can't have this 6 power 5 or more, because we will have more parameters. So we want to reduce data, the parameters, number of parameters. So what we did, each code, it's one black box. And the parameter here, we will have the output for the first one, it will be the input of second one, but here we will have the uncertainty. The problem that using the PCE, we assume that the parameters, answer parameters, have the independent are independent, but it's not the case. In general, it's not the case. So we need to decorrelate this thing, this output. So what we did, so we parameterize the output using reduced side. So we use an approximation splines. It's smooth, and I think the degree 3 of spline give us smoothness, a good smoothness. Once we have this new parameterization, we want to construct a new distribution for the second code. So what you did, just using the correlation matrix for the previous, for the output here, this correlation matrix, it will be decomposed on two matrices L by L transpose, and then the new R, it will be just computed by the inverse of L times Y. And we will use to have the cumulative distribution, we use the Rosenblatt transformation, and CowSpy provide this directly. So here, what we did, so the output of the first box, that will be input of the second box, we approximated using spline like this. So here, this is the basis function. So the support, it's just between 0 and 1. And now, instead to have here, for example, 100 of uncertain output, we will have just few that's uncertain parameters that control point here, red dot here. And we will use decoration and the Rosenblatt transformation, and we will compute the new distribution here for each control point. Here, just because I didn't, if we zoom, we can find the first 5 are Gaussian. It's around this point, for example, for this one and this one also. The last one, it's Dirac, because there is no uncertainty in the last, this one, it's imposed. So now we will have just 5 parameters, 5 distribution, and we will use again the same procedure in using the VQ and to have a new these statistics and output for the second model. And here, after the equilibrium model here, we plot just a profile of a magnetic field B, and we have this uncertainty here. And I did quick comparison between this approach, EQP2, and the first approach. If we have just single black box, and its order error, it's I think it's maximum error here. It's 10 minus 5, it's okay for this data. I don't know now if for other data, for more parameters, we will have more or no. It's under investigation, this part. And also, if you here, for example, we will have Sobol here. This one, it's very small, and they have discussion with Anna last time and also today, and maybe this one, because the Sobol is very, very small, we can also neglect it, and we'll have just few parameters in the input. So it will be another kind of reduction of the size. So for the conclusion now, it's so what we did now, we identify and implement the Q patterns. So we have 2 patterns. It's always no intrusive method for the multiscale workflow. Now we are just working with 3 codes. The third code, that is turbulence, we didn't touch it because what we did just with analytical code for turbulence. So we are exploring, this is the huge problem issue with this new code of turbulence. So we explore now the spline approximation to have less parameters, and also sparse grid and a grid. I know that in CowSpy they have this possibility, so it's basically we can have it in Emissive EQ. And also there is another one, is clustering. I had discussion with Dan last time in Amsterdam, and we want now to investigate more in this part. In collaboration with Vikma team, we are using pilot job integrated Emissive EQ library. I put in progress work, but now it's already done. I think you can also connect in the GitHub of Vikma toolkit, and you can also find the step-by-step for toy model, using toy model just Python code, or the Fusion code also. I think that in online today. And also the last thing I think I want to do is to use the database for that. I think now it's already done in this release to streamline the workflow of EQ and also to store the anti-query data, because we have a lot of data after every job. For example, to have descriptive statistics and also the sensitivity analysis, and also to run another job, another workflow. And it will be also the next in the future, the next time work now. So this is it. Thank you very much for your attention.